Table of contents for a subject titled Introduction to Environmental Chemistry. Table of contents. 1. Introduction to Environmental Chemistry. 1.1 Overview of Environmental Chemistry. 1.2 Importance of Environmental Chemistry in Sustainability. 1.3 Scope and applications of environmental chemistry. 2 Basic concepts in chemistry. 2.1 Atomic and molecular structure. 2.2 Chemical reactions and bonding. 2.3 Thermodynamics in environmental chemistry. 2.4 Kinetics and environmental processes. 3. The Earth's atmosphere and chemistry. 3.1 Composition of the atmosphere. 3.2 Air pollution, sources and effects. 3.3 Greenhouse gases and global warming. 3.4 Stratospheric ozone depletion. 4. Water and its chemical properties. 4.1 The water cycle. 4.2 Water pollution and treatment. 4.3 Chemical contaminants in water. 4.4 Acid rain and its environmental impact. 5. Soil chemistry and pollution. 5.1 Soil composition and structure. 5.2 Soil contaminants and remediation techniques. 5.3 Heavy metals and pesticides in soil. 5.4 Soil erosion and its environmental consequences. 6. Toxicology and environmental contaminants. 6.1 Toxic chemicals in the environment. 6.2 Bioaccumulation and biomagnification. 6.3 Environmental impact of pesticides and industrial waste. 6.4 Risk assessment and toxicity testing. 7. Green chemistry and sustainable practices. 7.1 Principles of green chemistry. 7.2 Renewable energy and green technologies. 7.3 Waste minimization and recycling. 7.4 Sustainable agriculture and environmental chemistry. 8. Environmental analytical techniques. 8.1 Sampling methods for environmental studies. 8.2 Analytical instrumentation in environmental chemistry. 8.3 Data interpretation and environmental modeling. 8.4 Case studies in environmental monitoring. 9. Climate change and environmental chemistry. 9.1 Science of climate change. 9.2 Environmental chemical contributions to climate change. 9.3 Mitigation and adaptation strategies. 9.4 International agreements and policies. 10. Current issues in environmental chemistry. 10.1 Emerging contaminants and their impact. 10.2 Environmental justice and chemistry. 10.3 The role of chemists in environmental protection. 10.4 Future directions in environmental chemistry. 11. Conclusion and future perspectives. 11.1 Summary of key concepts. 11.2 The role of environmental chemistry in global challenges. 11.3 Future research areas in environmental chemistry. 1. Introduction to environmental chemistry. Environmental chemistry is the study of the chemical processes occurring in the environment, including interactions between natural and anthropogenic, human-made substances. This field is crucial for understanding how chemicals affect ecosystems, human health, and the planet as a whole. It involves studying the behavior, distribution, and fate of chemicals in air, water, soil, and living organisms. 1.1 Overview of environmental chemistry. Environmental chemistry focuses on understanding how chemical substances interact with the environment. These interactions include how pollutants are released into the air, water, and soil, how they are transformed, and how they move through the environment. Environmental chemists also study the impact of chemicals on living organisms and ecosystems. This includes both harmful substances, such as toxins, and beneficial substances, like nutrients that sustain life. The study of environmental chemistry includes several key concepts. Chemical reactions in the environment. Chemical cycles, such as the nitrogen and carbon cycles. Toxicology, which examines the harmful effects of chemicals on living organisms. The movement of chemicals through the environment, or fate, and transport. 1.2 Importance of environmental chemistry in sustainability. Environmental chemistry plays a critical role in sustainability because it helps us understand how human activities affect the environment and how we can mitigate negative impacts. Some key contributions to sustainability include pollution control. Environmental chemistry helps in identifying and controlling pollutants, e.g., greenhouse gases, heavy metals, pesticides, to reduce their harmful impact on ecosystems and human health. Waste management. Through chemical analysis, we can develop methods to treat and recycle waste, reducing contamination of land and water resources. Green chemistry. This subfield emphasizes designing chemicals and processes that are environmentally friendly, using renewable resources, and minimizing waste and energy use. Climate change. Understanding the chemical interactions contributing to climate change, like greenhouse gas emissions, is essential for developing strategies to reduce global warming. Sustainability depends on balancing the demands of human activity with the health of the natural environment. Environmental chemistry provides the tools and knowledge necessary to manage and conserve natural resources, reduce pollution, and ensure environmental protection. 1.3 Scope and applications of environmental chemistry. The scope of environmental chemistry is vast and interdisciplinary, encompassing a wide range of scientific fields and applications. Water quality management. Environmental chemistry is crucial in assessing water pollution, determining water treatment strategies, and ensuring safe drinking water. Air pollution. The study of chemical pollutants in the atmosphere, such as particulate matter, ozone, and sulfur dioxide, is central to mitigating air quality issues. Soil contamination. Chemicals that pollute the soil can affect agricultural productivity and harm ecosystems. Environmental chemists work to identify these contaminants and develop remediation methods. Environmental monitoring and analysis, techniques such as chromatography and spectroscopy are used to detect and quantify pollutants in air, water, soil, and biological tissues. Remediation technologies. Environmental chemists develop and apply methods to clean up polluted environments, including bioremediation, using living organisms to remove pollutants, and chemical treatments. Through these applications, environmental chemistry contributes to a cleaner, healthier environment and helps address the challenges posed by pollution, climate change, and resource depletion. Two basic concepts in chemistry. Understanding the fundamental concepts of chemistry is crucial for environmental chemistry. These concepts provide the foundation for analyzing how chemicals behave in the environment and their impact on ecosystems, human health, and the climate. Below are the core concepts in chemistry that are key to environmental chemistry. 2.1 Atomic and molecular structure. Atoms are the basic building blocks of matter, consisting of a nucleus made of protons and neutrons, surrounded by electrons in orbitals. The arrangement and behavior of these atoms determine the chemical properties of substances. Atoms and elements. Each element is made up of atoms with a specific number of protons, which defines the element, e.g., carbon, oxygen, nitrogen. The periodic table organizes elements based on their atomic number and properties. Molecules. Molecules are formed when two or more atoms bond together. 4. Example: a water molecule, HO, consists of two hydrogen atoms and one oxygen atom. Isotopes. Some elements have isotopes, which are atoms with the same number of protons but different numbers of neutrons. Isotopes can be stable or radioactive, and their behavior is important in tracing environmental processes. Electron configuration. The arrangement of electrons around an atom's nucleus determines its chemical reactivity. Electrons in the outermost shell, valence electrons, are involved in chemical bonding. Chemical bonds. Atoms combine to form molecules through chemical bonds. There are three main types. O. Covalent bonds, formed when atoms share electrons, e.g., HO, CO. O. Ionic bonds, formed when one atom donates an electron to another, creating charged ions that attract each other, e.g., NaCl. O. Metallic bonds. In metals, atoms share electrons freely, creating a sea of electrons that gives metals their properties. Understanding atomic and molecular structures helps explain the behavior of chemicals in the environment, such as their ability to dissolve in water, how they bond to other substances, or how pollutants can accumulate in ecosystems. 2.2 Chemical reactions and bonding. Chemical reactions involve the breaking and forming of chemical bonds between atoms and molecules. These reactions are essential in environmental processes, such as the cycling of nutrients or the breakdown of pollutants. Types of chemical reactions. O. Combination reactions. Two or more substances combine to form a new compound, e.g., 2H plus O2HO. O. Decomposition reactions. A single compound breaks down into simpler substances, e.g., HOHO and O. O redox reactions involves the transfer of electrons between substances. This is key in processes like respiration, photosynthesis, and the degradation of pollutants. O acid-base reactions involves the transfer of protons, H ions, between substances. The pH of water, for example, affects the solubility and toxicity of many chemicals. O precipitation reactions, when two solutions are mixed, and an insoluble product, precipitate, forms. This is important in wastewater treatment and soil chemistry. Reaction rates, the speed at which a chemical reaction occurs depends on factors like temperature, concentration of reactants, and the presence of catalysts. Understanding reaction rates is crucial for predicting how quickly pollutants will degrade or how long they will persist in the environment. 2.3 Thermodynamics in environmental chemistry. Thermodynamics is the study of energy and its transformations. In environmental chemistry, thermodynamic principles help understand how energy changes during chemical reactions and physical processes, and how this affects the environment. First law of thermodynamics: energy cannot be created or destroyed, only converted from one form to another. This is important for understanding processes like the combustion of fossil fuels or the conversion of solar energy in photosynthesis. Second law of thermodynamics: the total entropy, disorder, of an isolated system always increases over time. This concept explains why some chemical reactions are spontaneous, they increase the system's entropy, while others require an input of energy. Gibbs free energy, delta G. This quantity indicates whether a reaction is thermodynamically favorable. If delta G is negative, the reaction is spontaneous. It helps determine the feasibility of chemical processes, such as pollutant degradation or the formation of ozone. Enthalpy, delta H. Enthalpy refers to the heat content of a system. Reactions that release heat, exothermic, or absorb heat, endothermic, can significantly influence the environment, e.g., climate change, ocean acidification. Thermodynamics is essential for understanding how pollutants behave in the environment, how energy is used or lost in chemical processes, and how reactions can be controlled or driven for sustainable purposes. 2.4 Kinetics and environmental processes. Kinetics is the study of the rates at which chemical reactions occur and the factors that influence those rates. In environmental chemistry, reaction kinetics helps us understand how fast chemicals are transformed or degraded in the environment. Reaction rate, the rate at which reactants are converted into products, is determined by the concentration of reactants, temperature, and the presence of catalysts. For example, the rate at which a pollutant decomposes in water depends on these factors. Environmental processes. O. Biodegradation, the breakdown of organic pollutants by microorganisms. Kinetic studies help assess how fast pollutants like oil or plastics degrade in natural systems. O. Atmospheric chemistry, reactions in the atmosphere, such as those involving greenhouse gases, ozone formation, and pollutants, are influenced by factors like sunlight, photochemical reactions, and temperature. Water treatment. Kinetics are critical in understanding how contaminants are removed from water, including chemical reactions in processes like chlorination or oxidation. Soil chemistry. Chemical reactions in soil, such as nutrient cycling or the movement of contaminants, are governed by reaction rates, affecting agricultural practices and environmental remediation strategies. Understanding kinetics is crucial for modeling environmental processes, predicting pollutant behavior, and developing strategies for cleaning up contaminated environments. Together, these basic concepts in chemistry form the backbone of environmental chemistry, providing insight into how chemicals move through and interact with natural systems, and offering solutions for minimizing environmental impacts and promoting sustainability. 3. The Earth's atmosphere and chemistry. The Earth's atmosphere is a critical component of the planet's environmental system. It not only provides the air necessary for life but also plays a key role in regulating temperature, protecting organisms from harmful solar radiation, and supporting processes like the water cycle. Environmental chemistry explores the composition, behavior, and changes in the atmosphere, particularly in relation to air pollution and climate change. 3.1 Composition of the atmosphere. The Earth's atmosphere is made up of a mixture of gases that envelop the planet. The primary components include nitrogen, and the most abundant gas, making up approximately 78% of the atmosphere. Nitrogen is inert under normal conditions and does not readily react with other substances. Oxygen, comprising around 21% of the atmosphere, oxygen is vital for respiration and combustion. Argon, a noble gas, making up about 0.93% of the atmosphere, with very limited reactivity. Carbon dioxide, CO, although it makes up only about 0.04% of the atmosphere. CO is crucial for regulating Earth's temperature through its role in the greenhouse effect. Water vapor, HO. The amount of water vapor varies significantly, from 0 to 4%. And it is important for weather patterns and the water cycle. Trace gases, this category includes methane, CH, ozone, O, nitrous oxide, NO, and others, each present in small concentrations but playing significant roles in atmospheric chemistry and climate processes. In addition to these gases, the atmosphere contains particulate matter, e.g., dust, smoke, and aerosols, which can affect air quality and weather patterns. 3.2 Air pollution, sources and effects. Air pollution is the presence of harmful substances in the atmosphere, often as a result of human activities. These pollutants can have serious health, environmental, and climatic consequences. Sources of air pollution. Natural sources, volcanic eruptions, wildfires, dust storms, and biological processes like methane emissions from wetlands. Anthropogenic sources. Small black square transportation, vehicles emit carbon monoxide, CO, nitrogen oxides. Hydrocarbons, and particulate matter. Small black square industry, factories, power plants, and refineries release sulfur dioxide, SO, nitrogen oxides, NO, carbon dioxide, CO, and particulate matter. Small black square agriculture, livestock produce methane, and fertilizers release nitrous oxide, NO, a potent greenhouse gas. Small black square residential heating, burning wood or coal in homes generates particulate matter and carbon monoxide. Effects of air pollution. Human health, pollutants like particulate matter, ground-level ozone, O, and carbon monoxide can cause respiratory problems, cardiovascular diseases, and other health issues. Ecosystem damage. Pollutants like sulfur dioxide and nitrogen oxides can acidify soils and water bodies, damaging plant life, aquatic ecosystems, and biodiversity. Visibility reduction. Smog and haze from pollutants reduce visibility and affect aesthetic and environmental quality. Climate change. Some pollutants, like black carbon and methane, contribute to warming by absorbing sunlight and increasing the greenhouse effect. The complexity of air pollution lies in the way pollutants interact with each other and the environment. Some pollutants have a direct effect, e.g., smog formation, while others lead to more complex consequences like acid rain or climate change. 3.3 Greenhouse gases and global warming. The greenhouse effect is a natural process that warms the Earth's surface. Greenhouse gases, GHGs, trap heat from the sun, preventing it from escaping back into space. However, human activities have increased the concentration of these gases in the atmosphere, leading to an enhanced greenhouse effect and global warming. Greenhouse gases. Carbon dioxide, CO, the most significant human-caused greenhouse gas. Primarily produced by the burning of fossil fuels, e.g., coal, oil, and natural gas, for energy, transportation, and industrial processes. Methane, a more potent greenhouse gas than CO, methane is released by livestock, landfills, wetlands, and the production of oil and gas. Nitrous oxide, NO, produced by agricultural practices, especially the use of synthetic fertilizers, as well as industrial processes. Fluorinated gases, synthetic gases used in refrigeration, air conditioning, and industrial processes, including hydrofluorocarbons, HFCs, perfluorocarbons, PFCs, and sulfur hexafluoride, SF. These gases are potent greenhouse gases with long atmospheric lifetimes. Impacts of global warming. Rising temperatures, increased greenhouse gas concentrations lead to higher global temperatures, which affect weather patterns, ecosystems, and human societies. Melting ice and rising sea levels. Warmer temperatures cause polar ice sheets and glaciers to melt, contributing to rising sea levels and threatening coastal communities. Changes in precipitation. Global warming can lead to altered weather patterns, including more frequent and intense storms, droughts, and flooding. Ocean acidification. increased CO absorption by the oceans lowers the pH, negatively affecting marine life, particularly coral reefs and shellfish. Efforts to mitigate global warming focus on reducing greenhouse gas emissions, transitioning to renewable energy sources, and enhancing carbon sequestration through reforestation and carbon capture technologies. 3.4 Stratospheric ozone depletion. The ozone layer, located in the stratosphere, plays a critical role in protecting life on Earth. By absorbing most of the sun's harmful ultraviolet, UV, radiation. However, human-made chemicals have caused damage to this protective layer, leading to ozone depletion. Ozone depletion mechanism. The depletion of ozone is primarily caused by human-made chemicals called ozone-depleting substances, ODs, especially chlorofluorocarbons, CFCs, halons, and other halogenated compounds. When released into the atmosphere, CFCs and similar chemicals slowly rise to the stratosphere, where ultraviolet radiation breaks them down, releasing chlorine, Cl, and bromine, Br, atoms. These halogens then catalytically destroy ozone molecules, O, converting them into oxygen molecules, O, and individual oxygen atoms, O. A single chlorine or bromine atom can destroy thousands of ozone molecules before being removed from the stratosphere. Consequences of ozone depletion. Increased UV radiation. Ozone depletion leads to higher levels of harmful UVB radiation reaching the Earth's surface. This can cause skin cancer, cataracts, and weakened immune systems in humans, as well as disrupt ecosystems, including marine plankton and crop growth. Changes in climate, ozone depletion and the warming of the lower atmosphere, due to increased greenhouse gases, are interconnected. These changes can alter atmospheric circulation patterns and impact weather systems. Montreal Protocol. To address ozone depletion, international agreements like the Montreal Protocol have been successful in reducing the use of ODs. Since the protocol's implementation, there have been signs of gradual recovery in the ozone layer, although full recovery will take several decades. Understanding the chemistry of the atmosphere is crucial for tackling global environmental challenges such as air pollution, climate change, and ozone depletion. Efforts to address these issues require international cooperation, technological innovation, and sustainable practices to protect the Earth's atmosphere and ensure a healthy planet for future generations. 4. Water and its chemical properties. Water is essential for life and plays a critical role in Earth's environmental systems. Its unique chemical properties make it a vital solvent, medium for chemical reactions, and regulator of temperature. In environmental chemistry, understanding water's behavior, contamination, and treatment is crucial for maintaining healthy ecosystems and human societies. 4.1 The water cycle. The water cycle, also known as the hydrological cycle, is a continuous process through which water circulates between the Earth's surface and the atmosphere. It involves several key processes that help maintain the availability of water across the planet. Evaporation. water from oceans, lakes, rivers, and other bodies of water turns into vapor and rises into the atmosphere. Plants also contribute to this process through transpiration, collectively called evapotranspiration. Condensation, as water vapor rises and cools, it condenses into liquid water, forming clouds. Precipitation, water falls from clouds in the form of rain, snow, sleet, or hail. Infiltration and runoff, some of the water seeps into the ground, infiltration, to replenish groundwater supplies, while the rest flows overland, runoff, into rivers, lakes, and oceans. Groundwater, water that has infiltrated the soil, is stored underground in aquifers. This water can eventually resurface through springs or be accessed via wells. The water cycle is essential for replenishing fresh water supplies and regulating the distribution of water across different ecosystems. It also helps distribute heat around the planet, contributing to climate regulation. 4.2 Water pollution and treatment. Water pollution occurs when harmful substances, such as chemicals, pathogens, or waste products, are introduced into water bodies. It threatens human health, wildlife, and ecosystems. Pollution can be classified into two main types. Point source pollution, pollution that originates from a specific, identifiable source, such as a wastewater discharge from factories, sewage treatment plants, or oil spills. Non-point source pollution, pollution that comes from diffuse sources, such as runoff from agricultural fields, urban areas, and construction sites. It often contains pesticides, fertilizers, heavy metals, and other contaminants. Treatment of polluted water. Water treatment is necessary to remove contaminants and make water safe for drinking, irrigation, and other uses. Water treatment typically involves several stages. 1. Coagulation and flocculation. Chemicals are added to water to form small particles, floc, that bind with impurities. 2. Sedimentation. The floc and contaminants settle to the bottom of the tank due to gravity. 3. Filtration. Water is passed through filters, e.g., sand or charcoal, to remove remaining particles. 4. Disinfection. Chlorine, ozone, or ultraviolet light is used to kill remaining pathogens and bacteria. 5. Advanced treatment. Some contaminants, such as heavy metals, pesticides, or pharmaceuticals, may require additional treatments, such as reverse osmosis or activated carbon filtration. Wastewater treatment also includes processes to treat industrial effluents, sewage, and agricultural runoff, often involving biological treatment, e.g., activated sludge processes, to break down organic matter. 4.3 Chemical contaminants in water. Various chemical pollutants can contaminate water sources, and they can have serious impacts on water quality, human health, and ecosystems. Heavy metals. Toxic metals like lead, Pb, mercury, Hg, arsenic, As, and cadmium, Cd, can enter water sources through industrial discharges, mining operations, and improper waste disposal. These metals can accumulate in aquatic organisms. leading to bioaccumulation and biomagnification, and can be harmful to both humans and wildlife. Pesticides and herbicides, chemicals used in agriculture to control pests and weeds, often end up in water bodies through runoff. These chemicals can contaminate drinking water supplies and harm aquatic life by disrupting ecosystems and causing algal blooms. Nutrients, nitrogen, N, and phosphorus, P, are essential for plant growth but can become pollutants when present in excess. They often enter water from agricultural runoff, fertilizers, wastewater effluents, and animal waste. Excess nutrients can cause eutrophication, leading to oxygen depletion, fish kills, and harmful algal blooms. Pharmaceuticals and personal care products, PPCPs, trace amounts of drugs, hormones, and personal care products can be found in water due to improper disposal, wastewater treatment limitations, and agricultural use of veterinary drugs. These substances can affect aquatic life and may contribute to antibiotic resistance. Organic pollutants, volatile organic compounds, VOCs, like benzene, trichloroethylene, and solvents from industrial and household sources can contaminate water. They can pose carcinogenic and toxic risks to humans and wildlife. Radionuclides, radioactive materials, such as radon or uranium, can enter water sources through natural processes or industrial activities like mining and nuclear waste disposal. Managing and monitoring these contaminants is critical to maintaining water quality and ensuring the health of ecosystems and people who rely on water resources. 4.4 Acid rain and its environmental impact. Acid rain refers to any form of precipitation, rain, snow, sleet, fog, that has a pH below 5.6. Primarily due to the presence of sulfuric acid, HSO, and nitric acid, HNO. These acids form when sulfur dioxide, SO, and nitrogen oxides, NO, released by burning fossil fuels, e.g., coal, oil, and gas, react with water vapor in the atmosphere. Formation of acid rain. 1. Sulfur dioxide, SO, emitted from industrial processes, power plants, and transportation. In the atmosphere, SO reacts with oxygen to form sulfur trioxide, SO, which then reacts with water to form sulfuric acid, HSO. 2. Nitrogen oxides, NO, emitted by vehicles, power plants, and agriculture. Nitrogen oxides combine with water to form nitric acid, HNO. Environmental impacts of acid rain. Soil acidification. Acid rain can lower the pH of soils, disrupting the availability of nutrients and minerals needed for plant growth. It also releases toxic metals like aluminum, which can harm plant roots and aquatic organisms. Water quality. Acid rain lowers the pH of water bodies, such as rivers and lakes, making them acidic. This harms aquatic life, particularly fish and amphibians, which have narrow pH tolerance ranges. Vegetation damage. Acid rain directly damages plant leaves and stems, impairs photosynthesis, and weakens plant defenses, making them more Susceptible to disease and environmental stress. O. Buildings and structures. Acid rain accelerates the degradation of buildings, monuments, and infrastructure made of limestone, marble, and other stone materials by reacting with the minerals and causing erosion. Mitigation. Reducing emissions of sulfur dioxide and nitrogen oxides through regulations, cleaner technologies, and the use of cleaner fuels has been effective in reducing acid rain. The Clean Air Act in the U.S. and similar regulations worldwide have contributed to significant reductions in acid rain. In summary, water is a vital and dynamic component of the Earth's systems, and understanding its chemical properties is essential for addressing water quality issues, pollution, and the broader environmental impacts such as acid rain. Environmental chemistry plays a key role in devising solutions for water treatment, pollutant management, and the conservation of water resources. 5. Soil chemistry and pollution. Soil is a fundamental component of terrestrial ecosystems, supporting plant growth, regulating water flow, and providing habitat for organisms. Soil chemistry is essential for understanding how nutrients, contaminants, and other substances interact within the soil, and how pollution can degrade soil health and function. In this section, we explore soil composition, contamination, and remediation, as well as the consequences of soil erosion. 5.1 Soil composition and structure. Soil is a complex mixture of mineral particles, organic matter, water, and air. Its composition and structure determine its ability to support plant growth and perform ecological functions. Mineral components. These include sand, silt, and clay. The relative proportions of these particles determine the soil's texture. O. Sand, coarse and large particles, drains water quickly, but has low nutrient holding capacity. O. Silt, fine particles, holds water and nutrients better than sand. O. Clay, very fine particles, retains water and nutrients well but has poor drainage. Soils are classified based on their texture, such as sandy, loamy, or clayey soil. Organic matter, decomposed plant and animal material, also known as humus, contributes to soil fertility by providing nutrients and improving soil structure. Organic matter enhances the soil's water-holding capacity and supports microbial life. Soil pH, which measures the acidity or alkalinity of the soil, influences nutrient availability. Most plants thrive in soils with a pH between 6 and 7, neutral, though some may prefer more acidic or alkaline conditions. Soil fertility. Fertility is determined by the availability of essential nutrients, e.g. nitrogen, phosphorus, potassium, and the soil's ability to retain and release these nutrients. Soil organic matter and microbial activity play a crucial role in nutrient cycling. Soil structure, the arrangement of soil particles into aggregates, which determines the soil's porosity and permeability. Well-structured soil has good aeration and water infiltration, while compacted soil may hinder root growth and water movement. Soil composition and structure are key to understanding how pollutants interact with the soil, how contaminants are retained or leached, and how soil functions in sustaining ecosystems. 5.2 Soil contaminants and remediation techniques. Soil contamination occurs when harmful substances, such as heavy metals, pesticides, industrial chemicals, and petroleum products, are introduced into the soil. These contaminants can disrupt soil health, reduce agricultural productivity, and pose risks to human and environmental health. Common soil contaminants. Heavy metals, lead, Pb, mercury, Hg, cadmium, Cd, arsenic, As, and chromium, Cr, are common pollutants from industrial, agricultural, and urban sources. Pesticides and herbicides, chemical compounds used in agriculture can persist in the soil and contaminate water supplies, affecting biodiversity and food safety. Petroleum products, spills or leaks from industrial or transportation activities can introduce hydrocarbons into the soil, harming plant and microbial life. Industrial chemicals, chemicals like solvents, polychlorinated biphenyls, PCBs, and other persistent organic pollutants, POPs, can accumulate in soils, impacting ecosystems. Remediation techniques. Physical remediation involves removing contaminated soil or isolating pollutants. For example, contaminated soil can be excavated and replaced, or treated in situ with technologies like soil washing, washing soil with water, or solvents to remove pollutants. Chemical remediation, chemical treatments, such as oxidation or reduction, can break down or transform contaminants into less harmful substances. For example, the use of potassium permanganate to degrade organic pollutants in the soil. Bioremediation uses microorganisms or plants to degrade or absorb contaminants. Plants, phytoremediation, or bacteria, bioremediation, can absorb or break down pollutants like heavy metals, organic solvents, and petroleum products. Bioventing involves using oxygen or nutrients to stimulate microbial activity in the soil to degrade organic contaminants. Stabilization/solidification, contaminated soil is mixed with chemicals to immobilize harmful substances and prevent them from leaching into groundwater. Each remediation technique is tailored to the type of contamination, the scale of the problem, and the specific characteristics of the contaminated site. 5.3 Heavy metals and pesticides in soil. Heavy metals and pesticides are some of the most concerning soil contaminants because of their toxicity, persistence, and potential for bioaccumulation in food chains. Heavy metals, these elements are naturally occurring but can be introduced into soils through industrial activities, e.g., mining, smelting, manufacturing. Agricultural practices, e.g., pesticides, fertilizers, and urban pollution. Toxicity, many heavy metals, such as lead, mercury, and cadmium, are toxic to plants, animals, and humans. They can accumulate in plant tissues and enter the food chain, posing risks to human health. Bioaccumulation, heavy metals can build up in living organisms over time, leading to harmful effects, such as developmental and neurological damage in humans and animals. Mobility. Some heavy metals can leach into groundwater, spreading contamination beyond the immediate area and affecting water quality. Pesticides. Pesticides and herbicides are commonly used in agriculture to control pests and weeds, but they can persist in the soil for years, affecting microbial and plant health. Persistence. Some pesticides, especially organochlorine compounds, are resistant to breakdown and remain in the soil for long periods, potentially harming non-target organisms. Ecosystem impact. Pesticides can disrupt soil microbial communities, which are essential for nutrient cycling and soil health, and can harm pollinators like bees, which are crucial for agriculture. Efforts to reduce heavy metal contamination and pesticide use include regulations on industrial emissions, the development of safer chemicals, and the promotion of organic farming practices that minimize chemical inputs. 5.4 Soil erosion and its environmental consequences. Soil erosion is the removal of the topsoil layer by wind, water, or human activity. Topsoil contains most of the soil's nutrients and organic matter, so its loss can degrade land and reduce agricultural productivity. Causes of soil erosion. Agriculture. Improper farming practices, such as overgrazing, monoculture, cropping, and plowing, can disturb the soil, making it more susceptible to erosion by wind and water. Deforestation. The removal of trees and vegetation reduces the soil's ability to retain moisture and protects it from wind and water erosion. Construction and urbanization. Development of land for cities, roads, and infrastructure can disturb soil and increase runoff, leading to erosion. Climate change. Increased rainfall intensity and wind patterns due to climate change can exacerbate erosion. Consequences of soil erosion. Loss of fertile soil. Erosion removes the topsoil, which is rich in nutrients and organic matter, leading to reduced soil fertility and crop yields. Water pollution. Eroded soil can carry sediments and pollutants, such as pesticides and fertilizers, into rivers and lakes, leading to water pollution and eutrophication. Desertification. In areas where erosion is severe, land may become barren and incapable of supporting plant life, contributing to the spread of deserts and the degradation of ecosystems. Reduced biodiversity. Soil erosion can lead to the loss of habitat for various species of plants, animals, and microorganisms that depend on the soil for survival. Prevention and mitigation. Erosion control practices. Measures such as contour plowing, terracing, planting cover crops, and creating windbreaks help protect soil from erosion. Reforestation. Planting trees and vegetation helps stabilize the soil and reduce the impact of wind and water erosion. Sustainable agriculture. Implementing sustainable farming practices, such as crop rotation, agroforestry, and reduced tillage, helps prevent soil degradation and erosion. In summary, soil chemistry plays a critical role in the function of terrestrial ecosystems and Agriculture. The contamination of soil with heavy metals, pesticides, and other pollutants poses serious environmental and health risks, while soil erosion exacerbates land degradation and pollution. Effective management and remediation techniques are crucial for protecting soil health and maintaining ecosystem services. 6. Toxicology and environmental contaminants. Toxicology is the study of harmful effects of chemicals on living organisms, and it plays a key role in understanding how environmental contaminants impact human health, ecosystems, and biodiversity. In this section, we will explore the presence and effects of toxic chemicals in the environment, their accumulation in organisms, and the processes used to assess and manage environmental risk. 6.1 Toxic chemicals in the environment. Toxic chemicals are substances that can cause harm to humans, animals, plants, and ecosystems even at relatively low concentrations. These chemicals can be naturally occurring or man-made and can enter the environment through various sources, including industrial processes, agricultural activities, transportation, and waste disposal. Types of toxic chemicals. Heavy metals. Toxic metals such as mercury, Hg, lead, Pb, cadmium, Cd, and arsenic, As, are naturally present in the Earth's crust but can be released into the environment through mining, industrial processes, and waste disposal. These metals are harmful to human health and wildlife, even in trace amounts. Persistent organic pollutants, POPs. These are synthetic chemicals, such as polychlorinated biphenyls, PCBs, dioxins, and pesticides, e.g., DDT, that persist in the environment for long periods due to their chemical stability. They accumulate in the food chain and pose long-term risks to ecosystems and human health. Pesticides and herbicides. These chemicals are used in agriculture to control pests and weeds but can be toxic to non-target species, including beneficial insects, wildlife, and aquatic organisms. Some pesticides, such as organophosphates, are highly toxic to humans and animals. Pharmaceuticals and personal care products, PPCPs. These chemicals, including antibiotics, hormones, and cosmetic ingredients, often end up in the environment through wastewater and runoff. They can disrupt ecosystems and contribute to the development of antibiotic resistance. Industrial chemicals. Many industrial chemicals, such as solvents, dyes, and plastics, e.g., bisphenol A, or BPA, can leach into the environment, contaminating water and soil and causing toxicity to both humans and wildlife. Toxic chemicals can affect organisms through direct exposure, e.g., inhalation, ingestion, or skin contact, or through contamination of food, water, and air. Understanding the sources, behavior, and effects of these chemicals is essential for managing environmental health risks. 6.2 Bioaccumulation and biomagnification. Bioaccumulation and biomagnification are processes through which toxic substances accumulate in organisms and move through the food chain. Bioaccumulation occurs when an organism absorbs a toxic substance faster than it can eliminate it. Over time, this leads to a higher concentration of the chemical within the organism's tissues. This process is especially significant for chemicals that persist in the environment, such as heavy metals and persistent organic pollutants, POPs. Example, mercury is a heavy metal that can bioaccumulate in the tissues of aquatic organisms. Fish, for example, may absorb mercury from water and food, leading to elevated concentrations of mercury in their bodies. Biomagnification. Biomagnification refers to the process by which toxic chemicals become more concentrated as they move up the food chain. Organisms at higher trophic levels, such as predators, consume multiple prey that contain toxic chemicals, leading to progressively higher concentrations of the toxins in their bodies. Example, in aquatic food webs, small organisms like plankton absorb pollutants like DDT. These are consumed by small fish, which are then eaten by larger fish, birds, or mammals. As a result, top predators, such as eagles or humans, may have significantly higher levels of pollutants like DDT or mercury. Bioaccumulation and biomagnification have serious consequences for ecosystem health, as they can lead to the poisoning of species, disruption of reproductive processes, and long-term health effects. These processes also pose risks to human health, particularly for those who consume contaminated seafood or rely on animals as food sources. 6.3 Environmental impact of pesticides and industrial waste. Both pesticides and industrial waste have significant environmental impacts, contributing to pollution, ecosystem degradation, and risks to human health. Pesticides. Toxicity to non-target species. Pesticides can have lethal or sublethal effects on non-target organisms, including beneficial insects, e.g., bees and butterflies, birds, aquatic organisms, and soil microorganisms. For example, insecticides like neonicotinoids are known to affect pollinators, contributing to declines in bee populations. Pesticide resistance. Overuse or misuse of pesticides can lead to the development of resistance in pest populations, making them more difficult to control and leading to increased pesticide use, which further harms the environment. Pollution of water bodies. Pesticides can leach into groundwater or be carried by runoff into rivers, lakes, and oceans, where they contaminate water sources and harm aquatic ecosystems. This can lead to the decline of fish populations, algal blooms, and reduced water quality for human consumption. Industrial waste. Toxic chemical release. Industrial activities, such as manufacturing, mining, and oil extraction, often generate hazardous waste, including heavy metals, solvents, and petrochemicals, which can contaminate soil, water, and air. These pollutants can degrade habitats and ecosystems, making them uninhabitable for many species. Air pollution. Industrial emissions can release toxic chemicals into the air, such as volatile organic compounds, VOX, sulfur dioxide, SO, and nitrogen oxides, No, which contribute to smog, acid rain, and health problems in humans and animals. E-waste, the improper disposal of electronic waste, e-waste, releases hazardous chemicals like lead, cadmium, and mercury into the environment. These substances can leach into the soil and groundwater, impacting both human and environmental health. Addressing the environmental impact of pesticides and industrial waste requires the implementation of stricter regulations, cleaner technologies, and more sustainable practices in agriculture and industry. 6.4 Risk Assessment and Toxicity Testing. Risk assessment and toxicity testing are key tools used to evaluate the potential harm of chemicals and pollutants on human health and the environment. These processes help inform policy decisions, environmental regulations, and public health measures. Risk assessment. Risk assessment is a systematic process used to evaluate the potential adverse effects of a substance or exposure. It typically involves 4 steps. 1. Hazard identification, determining whether a substance has the potential to cause harm to human health or the environment. 2. Dose response assessment, understanding the relationship between the amount of exposure to a substance and the severity of the harmful effects. 3. Exposure assessment, estimating the level of exposure to a chemical based on its concentration in the environment and the pathways through which humans or wildlife might come into contact with it. 4. Risk characterization, combining the information from the previous steps to estimate the risk of harm and determine whether action is necessary to mitigate that risk. Toxicity testing. Toxicity testing involves experimental studies to determine the harmful effects of a substance on living organisms. These tests can include acute toxicity testing, determines the immediate toxic effects of a substance following a single exposure. Chronic toxicity testing, assesses the long-term effects of continuous or repeated exposure to a substance over weeks, months, or even years. Genotoxicity testing, evaluates the potential of a chemical to damage genetic material and cause mutations, cancer, or other genetic disorders. Ecotoxicity testing, studies the effects of chemicals on ecosystems, including plants, animals, and microorganisms. This testing helps determine the potential for chemicals to disrupt food webs or reduce biodiversity. Toxicity testing can be done using laboratory animals, in vitro, cell-based methods, or computer simulations. While animal testing remains an important part of toxicity testing, there is increasing interest in alternative methods that reduce animal use and rely on human-based models or advanced technologies. Conclusion. Toxicology and environmental contaminants are critical areas of study for understanding the risks posed by pollutants in our environment. Bioaccumulation and biomagnification can lead to dangerous levels of toxins in ecosystems and food chains. The environmental impacts of pesticides and industrial waste can have far-reaching consequences, disrupting ecosystems, poisoning wildlife, and affecting human health. Risk assessment and toxicity testing provide essential tools for understanding and mitigating these risks, ensuring a safer and more sustainable environment for current and future generations. 7. Green chemistry and sustainable practices. Green chemistry is an innovative approach to chemical processes that minimizes the negative impact on the environment, reduces waste, and promotes sustainability. It aims to design chemical products and processes that are environmentally friendly, economically viable, and safe for human health. Sustainable practices, including renewable energy, waste minimization, and sustainable agriculture, are essential to achieving long-term environmental protection and resource conservation. In this section, we will explore the principles of green chemistry and how it intersects with renewable energy, waste management, and sustainable agriculture. 7.1 Principles of Green Chemistry. Green chemistry refers to the design of chemical products and processes that reduce or eliminate the use and generation of hazardous substances. The following principles guide the field of green chemistry. 1. Prevention. It is better to prevent waste than to treat or clean it up later. This principle emphasizes designing chemical processes that avoid the creation of waste from the outset. 2. Atom economy. Reactions should be designed to maximize the use of all materials involved. The goal is to reduce waste by ensuring that the maximum amount of atoms from the reactants are incorporated into the desired product, minimizing byproducts. 3. Less hazardous chemical synthesis. Chemical reactions should be designed to minimize the use of toxic and hazardous chemicals, both in terms of reactants and products, to reduce environmental and health risks. 4. Design for energy efficiency. Chemical processes should be designed to operate at ambient temperature and pressure whenever possible to reduce energy consumption and environmental impact. 5. Use of renewable feedstocks. Whenever feasible, renewable raw materials should be used in place of non-renewable resources, e.g., using biomass or plant-based materials instead of fossil fuels. 6. Reduce derivatives. The use of auxiliary substances such as solvents, separation agents, and protecting groups should be minimized or avoided to reduce environmental burden. 7. Catalysis. Use catalytic processes rather than stoichiometric ones to increase reaction efficiency and reduce the amount of chemicals needed. 8. Design for degradation. Products should be designed so that they can be broken down into harmless substances after their useful life ends, preventing long-term environmental harm. 9. Real-time monitoring. Monitoring the reaction as it occurs helps identify and control the process to ensure safety, efficiency, and minimal waste generation. 10. Safer chemistry for accident prevention. Designing chemical processes with built-in safety features to prevent accidents, spills, or releases of harmful substances. These principles guide the development of environmentally friendly chemicals, materials, and processes, helping to reduce pollution, conserve resources, and promote sustainability. 7.2 Renewable energy and green technologies. Renewable energy and green technologies play a vital role in reducing environmental pollution and mitigating climate change. These technologies harness energy from sources that are naturally replenishing and cause minimal harm to the environment. Solar energy. Solar power captures energy from the sun through photovoltaic cells. or concentrated solar power systems. Solar energy is abundant, sustainable, and produces no direct emissions, making it one of the most important renewable energy sources in the transition to a low-carbon economy. Wind energy. Wind power generates electricity through turbines that convert the kinetic energy of wind into mechanical energy. Wind energy is a clean and renewable source of power that can be harnessed on both large and small scales. Hydropower. Hydropower generates electricity by harnessing the energy of flowing water, typically through dams or other water flow mechanisms. While hydropower is renewable, its environmental impact, including the disruption of aquatic ecosystems, needs to be carefully considered. Geothermal energy. Geothermal power uses the heat from beneath the Earth's surface to generate electricity and provide heating. It is a stable and reliable energy source that produces very low emissions. Biomass energy. Biomass energy is derived from organic materials, such as wood, agricultural waste, and algae, that can be burned or converted into biofuels. Biomass is renewable, but its sustainability depends on how the materials are sourced and processed. Green technologies. These technologies aim to reduce the environmental footprint of various industries. Some key examples include energy-efficient buildings. Technologies like insulation, energy-efficient lighting, and smart HVAC systems help reduce energy consumption in buildings. Electric vehicles. EVs reduce the reliance on fossil fuels and lower emissions in the transportation sector. Carbon capture and storage. CCS technologies capture carbon dioxide, CO, from industrial processes and store it underground to prevent it from entering the atmosphere. Green manufacturing, incorporating energy-efficient machinery, waste minimization practices, and sustainable sourcing of raw materials into industrial production processes. Renewable energy and green technologies are critical for reducing reliance on fossil fuels, lowering greenhouse gas emissions, and transitioning toward a more sustainable future. 7.3 Waste minimization and recycling. Waste minimization and recycling are key components of sustainable practices, aiming to reduce the amount of waste generated and to repurpose materials in ways that reduce the need for virgin resources. Waste minimization. Source reduction, preventing waste from being generated in the first place. Through better design, more efficient processes, and reduced consumption of raw materials. Process optimization, streamlining industrial processes to minimize waste generation, energy consumption, and resource use. This may involve adopting lean manufacturing principles, improving product design, or using less toxic substances. Product life extension, designing products that are durable, reparable, or modular, which reduces the need for frequent replacement and encourages reuse. Recycling. Recycling of materials. Recycling involves the collection, processing, and conversion of waste materials into new products. Common materials for recycling include paper, plastics, metals, and glass. Electronic waste recycling. As the use of electronics increases, e-waste recycling has become a critical practice. Recycling electronics recovers valuable metals like gold, silver, and copper, and reduces harmful environmental impacts associated with improper disposal. Organic waste. Organic waste such as food scraps and yard waste can be composted to create nutrient-rich soil for agriculture, reducing landfill waste and greenhouse gas emissions from decomposing organic matter. Circular economy. A circular economy seeks to minimize waste by designing products that can be reused, refurbished, or recycled back into the supply chain, rather than following a linear take-make-dispose model. Recycling and waste minimization are vital to reducing the environmental burden of landfills, conserving resources, and lowering pollution. 7.4 Sustainable agriculture and environmental chemistry. Sustainable agriculture seeks to meet the growing demand for food while preserving the environment, promoting biodiversity, and ensuring long-term agricultural productivity. It incorporates environmentally friendly practices and relies on an understanding of environmental chemistry to manage soil, water, and pest populations sustainably. Soil health and fertility. Sustainable agriculture focuses on maintaining and improving soil health by minimizing soil erosion, reducing chemical inputs, and enhancing soil organic matter. Techniques such as crop rotation, agroforestry, and reduced tillage help preserve soil structure, fertility, and biodiversity. Organic fertilizers. The use of organic fertilizers, e.g., compost, manure, instead of synthetic chemical fertilizers helps maintain soil health and reduces the risk of nutrient pollution in water bodies. Water management. Sustainable irrigation practices reduce water wastage, enhance water use efficiency, and minimize the impact on local water resources. Techniques such as drip irrigation, rainwater harvesting, and the use of drought-resistant crops help ensure water conservation in agriculture. Integrated pest management, IPM. IPM combines biological, cultural, and chemical methods to control pests in a sustainable manner. It reduces the reliance on harmful pesticides, promotes biodiversity, and uses environmentally friendly alternatives like biocontrol agents, e.g., predators, parasites. Agroecology. Agroecology applies ecological principles to agricultural systems, focusing on biodiversity, soil health, and sustainable land management practices. It encourages the use of native plants, reduces chemical inputs, and supports resilient farming systems that can adapt to changing environmental conditions. Climate-smart agriculture. Climate-smart agriculture promotes practices that help farmers adapt to climate change, such as planting climate-resilient crops, diversifying crops, and reducing greenhouse gas emissions from farming activities. Sustainable agriculture integrates environmental chemistry, soil science, and ecosystem management to ensure that agricultural practices support both food production and environmental stewardship. Conclusion. Green chemistry and sustainable practices provide the framework for creating Environmentally responsible solutions across industries. By focusing on reducing waste, using renewable resources, and adopting energy-efficient technologies, we can mitigate environmental damage and foster a more sustainable future. Green chemistry principles guide industries toward safer, more sustainable practices, while renewable energy, waste minimization, and sustainable agriculture offer practical tools for addressing the challenges of resource depletion, pollution, and climate change. Embracing these practices will be key to achieving a sustainable and thriving planet for future generations. 8. Environmental analytical techniques. Environmental analytical techniques are crucial for assessing the quality of air, water, soil, and ecosystems. These methods allow scientists to detect, quantify, and analyze pollutants and other substances in the environment. By employing various sampling methods, advanced instrumentation, and data interpretation techniques, we can better understand environmental processes, pollution sources, and the impact of human activities on natural systems. In this section, we explore the key methods and tools used in environmental chemistry and monitoring. 8.1 Sampling methods for environmental studies. Sampling is the process of collecting representative samples from the environment for analysis. It is the first critical step in environmental monitoring and is essential to ensure that the collected data accurately reflect the condition of the environment. The choice of sampling method depends on the type of study, the substances being analyzed, and the characteristics of the environmental medium. Air sampling. Passive sampling relies on the natural diffusion of airborne chemicals into a collector over time. Passive samplers are typically simple and cost-effective tools, such as diffusion tubes and sorbent materials. Active sampling involves the use of a pump to draw air through a filter or sorbent material, collecting particles or gases for subsequent analysis. This method is more precise but requires more complex equipment. Examples: sampling for particulate matter, PM, volatile organic compounds, VOX, and greenhouse gases like carbon dioxide and methane. Water sampling. Grab sampling involves collecting a single sample at a specific point in time. This method is useful for analyzing short-term variations in water quality. Composite sampling combines multiple samples taken over a period, e.g., several hours or days, to account for variations in water quality over time and provide a more representative sample. In situ sampling, collecting water samples using instruments or devices that measure parameters, e.g., pH, dissolved oxygen, temperature, directly in the field. This helps reduce sample contamination and preserve sample integrity. Soil sampling. Random sampling involves collecting samples from various points in an area to obtain a representative composite sample. This method is commonly used for large or heterogeneous areas. Systematic sampling involves taking samples at regular intervals or from a grid pattern, which can provide more precise data for specific analyses, e.g., soil contamination studies. Core sampling involves using a tube or auger to obtain a vertical profile of the soil, useful for studying soil structure, composition, and contamination at different depths. Biological sampling. Benthic sampling, collecting organisms from the bottom of water bodies, e.g., rivers, lakes, to assess water quality based on the presence and health of aquatic organisms like benthic macroinvertebrates. Bioaccumulation studies, sampling organisms, e.g., fish, shellfish, to study the accumulation of pollutants in biological tissues and their potential transfer through the food chain. Proper sampling methods ensure that the data collected are reliable and representative of the environmental conditions being studied. The choice of method depends on the nature of the environment and the objectives of the study. 8.2 Analytical instrumentation in environmental chemistry. Analytical instrumentation refers to the tools and devices used to measure and analyze environmental samples for various substances, including pollutants, trace elements, and organic compounds. Some common analytical techniques include spectroscopy, atomic absorption spectroscopy, AAS, used to measure the concentration of metals and trace elements in environmental samples, such as water, soil, and air. AAS works by measuring the absorption of light by atoms in the sample. Inductively coupled plasma mass spectrometry, ICP-MS, a highly sensitive technique for detecting and quantifying metals and metalloids at trace levels in various environmental samples. Ultraviolet visible spectroscopy, UV-vis, used to analyze organic and inorganic compounds based on their absorption of ultraviolet or visible light. UV-vis can detect pollutants like nitrates, sulfates, and some organic contaminants. Chromatography. Gas chromatography, GC, separates and analyzes volatile compounds in air, water, and soil samples. GC is commonly used to measure pollutants like VOX, pesticides, and industrial chemicals. Liquid chromatography, LC, used to separate and quantify non-volatile compounds in complex environmental matrices, such as water, soil extracts, and biological samples. High-performance liquid chromatography, HPLC, a more advanced form of liquid chromatography that offers higher resolution and sensitivity. HPLC is commonly used for detecting organic pollutants and pharmaceuticals in environmental samples. Electrochemical analysis. Ion selective electrodes, ICs, used to measure specific ions, e.g., pH, nitrate, fluoride, in environmental water and soil samples. ICs are often portable and can be used in field testing. Voltammetry measures the electrical current generated by a chemical reaction to analyze the concentration of metal ions and other environmental pollutants in water and soil. Mass spectrometry, MS, a powerful analytical technique used for identifying and quantifying trace levels of contaminants in complex environmental samples. Coupled with chromatography, GCMS or LCMS, mass spectrometry can identify organic pollutants, pesticides, and pharmaceuticals. Spectrophotometry, measures the intensity of light at specific wavelengths to quantify the concentration of various pollutants in air, water, or soil samples. The selection of analytical instrumentation depends on the type of substance being analyzed, the required sensitivity, and the matrix of the environmental sample, e.g., solid, liquid, or gas. 8.3 Data interpretation and environmental modeling. Data interpretation and environmental modeling are essential for understanding and predicting environmental processes and the behavior of contaminants. Data interpretation. Statistical analysis. Environmental data often involve large data sets that require statistical analysis to detect trends, patterns, and relationships. Techniques such as regression analysis, variance analysis, and multivariate analysis are commonly used to interpret complex environmental data. Comparative analysis, comparing data collected from different sites, times, or conditions helps identify pollution sources, environmental changes, or the effectiveness of pollution control measures. Quality control, ensuring the accuracy and precision of environmental data, involves implementing quality control procedures, such as calibration, replication, and the use of control samples. Environmental modeling. Transport models, used to predict the movement of pollutants through air, water, and soil. These models help understand how contaminants spread over time and space, which is crucial for assessing environmental risks and planning remediation efforts. Ecosystem models simulate the interactions between various components of an ecosystem, including organisms, pollutants, and environmental variables. These models help assess the impact of pollutants on biodiversity, ecosystem health, and food webs. Exposure assessment models, used to estimate human exposure to environmental pollutants, taking into account factors such as pollutant concentration, duration of exposure, and pathways, e.g., inhalation, ingestion, dermal contact. Climate and climate change models, used to predict the impact of pollutants and greenhouse gases on climate patterns, global temperatures, and regional climate change. Environmental modeling relies on accurate data and mathematical simulations to predict the movement and effects of pollutants, providing valuable insights for policymaking and environmental management. 8.4 Case studies in environmental monitoring. Case studies provide practical examples of how environmental monitoring and analytical techniques are applied in real-world situations. Some notable case studies include water quality monitoring, monitoring the levels of pollutants, such as heavy metals, nutrients, e.g., nitrates, phosphates, and pathogens in rivers, lakes, and groundwater. For example, the monitoring of water quality around industrial sites can identify sources of contamination and inform water treatment strategies. Air pollution studies, monitoring air quality in urban and industrial areas to assess the concentration of pollutants such as particulate matter, PM, nitrogen oxides, NO, sulfur dioxide, SO, and ozone. This data is crucial for public health studies and formulating air quality standards and regulations. Oil spill remediation. After an oil spill, monitoring and analyzing the environmental impact on water, soil, and biota is essential. Techniques like GCMS and chromatography are used to track the spread of hydrocarbons and assess the effectiveness of cleanup efforts. Ecosystem health assessment, case studies of ecosystems affected by pollution, e.g., acid rain, pesticide runoff, or industrial discharge, can show the impacts on biodiversity and ecosystem services. Monitoring species diversity, soil health, and water quality helps evaluate ecosystem recovery. Climate change impact assessment, monitoring greenhouse gas emissions, air temperature, and ocean acidification provides valuable data to assess the impacts of climate change. This data is used to predict future climate scenarios and inform mitigation strategies. In conclusion, environmental analytical techniques are essential for understanding environmental contamination, monitoring pollutants, and predicting the impacts of human activities on natural systems. Sampling, advanced instrumentation, data analysis, and environmental modeling provide the tools needed for informed decision-making and effective environmental management. Case studies illustrate how these techniques are applied to address real-world challenges, from pollution control to climate change. Mitigation. 9. Climate change and environmental chemistry. Climate change refers to long-term alterations in temperature, precipitation, and other atmospheric conditions on Earth. It is driven by both natural processes and human activities, with the latter playing an increasingly dominant role due to emissions of greenhouse gases, GHGs, and other pollutants. Environmental chemistry is central to understanding the chemical processes behind climate change, its drivers, and the strategies needed for mitigation and adaptation. In this section, we will explore the science of climate change, the chemical contributions to the process, the strategies to mitigate and adapt to it, and international policies aimed at combating its impacts. 9.1 Science of climate change. The science of climate change is based on understanding the Earth's atmosphere, the greenhouse effect, and how human activities influence the balance of gases that regulate Earth's temperature. The greenhouse effect is a natural process by which certain gases trap heat in the atmosphere, keeping the planet warm enough to support life. However, human activities, particularly the burning of fossil fuels, deforestation, and agricultural practices, have significantly increased the concentrations of greenhouse gases in the atmosphere, intensifying the greenhouse effect and leading to global warming. Greenhouse gases, GHGs. Carbon dioxide, CO. The most significant GHG, produced by burning fossil fuels, coal, oil, natural gas, for energy, transportation, and industrial processes. Methane, CH. A potent GHG released by livestock digestion, rice paddies, landfills, and natural gas extraction. Nitrous oxide, NO. Emitted by agricultural practices, fossil fuel combustion, and industrial activities. Fluorinated gases, a group of synthetic gases, e.g., HFCs, PFCs, SF, used in industrial applications that have high global warming potentials, GWPs. Radiative forcing, this refers to the change in the balance between incoming solar radiation and outgoing infrared radiation due to the presence of GHGs in the atmosphere. An increase in radiative forcing leads to a rise in global temperatures, which in turn leads to climate disruptions. Global temperature rise. Since the late 19th century, global surface temperatures have risen by approximately 1.2 degrees Celsius, as of 2021. This increase in temperature has led to more extreme weather events, rising sea levels, and shifts in ecosystems. Climate models. Climate models are mathematical representations of the Earth's climate system that simulate how different variables, e.g., GHG concentrations, solar radiation, ocean currents, interact and influence global temperatures and climate patterns. These models are essential tools for predicting future climate scenarios and understanding the potential impacts of climate change. 9.2 Environmental chemical contributions to climate change. Environmental chemistry plays a significant role in both the causes and consequences of climate change. Several chemical processes directly and indirectly contribute to the buildup of greenhouse gases and their subsequent impact on global temperatures. Fossil fuel combustion. The burning of fossil fuels for energy production, transportation, and industrial processes releases large amounts of CO and other GHGs into the atmosphere. The combustion process involves the reaction of carbon-based fuels, coal, oil, natural gas, with oxygen, producing carbon dioxide and water. Coal combustion. Coal-burning power plants release significant amounts of CO, as well as sulfur dioxide, SO, nitrogen oxides, NO, and particulate matter, contributing to both air pollution and climate change. Deforestation and land use changes. Deforestation leads to the release of stored carbon in trees and soil as CO. Forests act as carbon sinks, absorbing CO from the atmosphere. When forests are cleared or burned, this carbon is released back into the atmosphere, exacerbating global warming. Agricultural practices. Practices such as plowing, irrigation, and the use of fertilizers release GHGs like methane, CH, from livestock and rice fields, and nitrous oxide, NO, from synthetic fertilizers. These gases have higher global warming potential than CO. Industrial processes. Industrial processes such as cement production, aluminum manufacturing, and refrigeration contribute to climate change through the release of GHGs like CO, methane, and fluorinated gases. Cement production. The chemical reaction of limestone, CaCO, with heat during cement production releases large amounts of CO. The process also requires significant energy, often derived from fossil fuels. Fluorinated gases. These synthetic gases, including hydrofluorocarbons, HFCs, and perfluorocarbons, PFCs, are used in refrigerants and industrial applications. Though present in small concentrations, their global warming potential is thousands of times greater than that of CO. Chemical feedback loops. O positive feedbacks, certain chemical processes in the atmosphere and ecosystems create positive feedback loops that accelerate climate change. For example, the melting of Arctic ice reduces the Earth's albedo reflectivity, causing more solar radiation to be absorbed by the oceans and further warming the planet. O methane release, thawing permafrost in Arctic regions can release stored methane, a potent GHG, into the atmosphere, further exacerbating warming. 9.3 Mitigation and Adaptation Strategies. Mitigation and adaptation are two main approaches for addressing the challenges of climate change. Mitigation involves reducing or preventing the emission of greenhouse gases to limit the severity of climate change. Key mitigation strategies include renewable energy, transitioning from fossil fuels to renewable sources of energy such as solar, wind, hydro, and geothermal power can significantly reduce CO emissions. Energy efficiency, improving the energy efficiency of buildings, industrial processes, and transportation systems can reduce energy consumption and emissions. Carbon capture and storage, CCS. CCS involves capturing CO emissions from industrial processes or power plants and storing them underground in geological formations to prevent them from entering the atmosphere. Reforestation and afforestation, planting trees and restoring forests can enhance carbon sequestration, as trees absorb CO during photosynthesis. Forest management practices can also reduce emissions from deforestation and forest degradation. Sustainable agriculture, adopting sustainable farming practices, such as no-till farming, crop rotation, and organic farming, can reduce GHG emissions from agriculture and increase carbon storage in soil. Carbon pricing, policies like carbon taxes and cap-and-trade systems create economic incentives for industries to reduce their carbon emissions. Adaptation involves adjusting to the effects of climate change that are already occurring or are expected to occur. Key adaptation strategies include climate-resilient infrastructure, building infrastructure that can withstand extreme weather events, such as flooding, heat waves, and hurricanes. This may involve reinforcing buildings, roads, and bridges, or improving stormwater management systems. Water management, developing strategies for managing water resources in the face of changing precipitation patterns and droughts, including water conservation, the construction of reservoirs, and the use of efficient irrigation technologies. Ecosystem protection, protecting and restoring ecosystems like wetlands, mangroves, and coral reefs that provide natural barriers against flooding and storm surges while supporting biodiversity. Disaster preparedness, developing early warning systems, evacuation plans, and emergency response strategies to protect vulnerable communities from the impacts of climate change. 9.4 International agreements and policies. International cooperation is essential to address the global challenge of climate change. Several agreements and policies aim to curb emissions, promote sustainable development, and protect vulnerable populations. The Paris Agreement, 2015. The Paris Agreement, adopted by nearly 200 countries at the 21st Conference of the Parties, 21 Colombian pesos, is a legally binding treaty aimed at limiting global temperature rise to well below 2 degrees Celsius above pre-industrial levels, with an aspiration to limit it to 1.5 degrees Celsius. Countries are required to submit nationally determined contributions, NDCs, outlining their efforts to reduce emissions, enhance climate resilience, and increase climate finance. Kyoto Protocol, 1997. The Kyoto Protocol was the first international treaty aimed at reducing GHG emissions, with legally binding targets for developed countries. Although the protocol was a step forward, its effectiveness was limited by the non-participation of major emitters like the United States and the lack of legally binding targets for developing nations. United Nations Framework Convention on Climate Change, UNFUC. The UNFUC is the main international body overseeing climate negotiations and policy development. It serves as the foundation for international climate agreements, including the Paris Agreement. The UNFUC also facilitates ongoing negotiations and conferences such as the annual COP meetings. Climate finance. Financial support for developing countries is a key component of international climate agreements. The Green Climate Fund, GCF, was established to help developing countries mitigate and adapt to climate change through financial assistance and technology transfer. Carbon trading and emission reduction mechanisms. Emission trading systems, such as the European Union Emissions Trading System, EU ETS, allow countries and industries to buy and sell emission allowances to meet their carbon reduction targets. These market-based mechanisms provide economic incentives for emissions reductions. Conclusion. Climate change is one of the most pressing challenges of our time, with significant impacts on ecosystems, human health, and the global economy. Environmental chemistry provides critical insights into the chemical processes driving climate change, from the burning of fossil fuels to the release of greenhouse gases and the chemical feedback loops that amplify warming. Mitigation and adaptation strategies are essential to address both the causes and consequences of climate change, while international agreements and policies play a vital role in fostering global cooperation to reduce emissions, increase climate resilience, and protect vulnerable populations. Addressing climate change requires a concerted effort from individuals, industries, governments, and international organizations to build a sustainable and resilient future for all. 10 Current issues in environmental chemistry. Environmental chemistry is continuously evolving as new challenges arise in response to changing environmental conditions, industrial practices, and societal needs. Understanding and addressing these challenges requires innovative scientific approaches and a deeper commitment to sustainability and environmental justice. In this section, we explore some of the most pressing current issues in environmental chemistry, including emerging contaminants, environmental justice, the role of chemists in environmental protection, and future directions for the field. 10.1 Emerging contaminants and their impact. Emerging contaminants are substances that are not commonly monitored but are increasingly found in the environment due to human activity. These contaminants often come from industrial, agricultural, and pharmaceutical sources, and they pose significant challenges due to their persistence, toxicity, and the complexity of managing them. Pharmaceuticals and personal care products, PPCPs. These include drugs, hormones, antibiotics, and cosmetics that enter the environment through wastewater discharge, leachate from landfills, or agricultural runoff. PPCPs can accumulate in aquatic ecosystems and may disrupt the hormonal systems of wildlife, as well as potentially affecting human health. Per and polyfluoroalkyl substances, PFAS. PFAS are a group of synthetic chemicals used in water and stain-resistant products, firefighting foams, and many industrial applications. Known as forever chemicals because of their persistence in the environment and human body, PFAS are highly toxic and have been linked to health issues such as cancer, liver damage, and immune system disruption. Nanomaterials. Nanomaterials, including nanoparticles and nanocomposites, are increasingly used in a variety of products ranging from electronics to medicine. While they have many beneficial applications, their small size and reactivity can lead to unintended environmental impacts. These materials can accumulate in soil, water, and organisms, and their long-term effects on human health and ecosystems are still not fully understood. Microplastics. Microplastics, which are tiny plastic particles, less than 5 mm in diameter, originating from larger plastic debris, clothing fibers, and other sources, are a significant environmental concern. They are widely distributed in marine and terrestrial environments and can be ingested by aquatic organisms, entering the food chain. Microplastics have been found to carry toxic chemicals and pathogens, presenting risks to both ecosystems and human health. Pharmaceutical resistance. The release of antibiotics into the environment contributes to the growing problem of antibiotic resistance. When antibiotics are present in water sources, they promote the growth of resistant bacteria, which can lead to reduced effectiveness of medications and contribute to public health risks. The detection, monitoring, and removal of emerging contaminants from environmental media such as water, soil, and air are significant challenges for environmental chemistry. Research into more sustainable alternatives, better waste treatment practices, and regulatory frameworks is needed to mitigate their impact. 10.2 Environmental justice and chemistry. Environmental justice focuses on the fair distribution of environmental benefits and burdens, especially in marginalized communities that often bear disproportionate environmental harm. Chemists play an essential role in understanding, addressing, and advocating for solutions to environmental disparities. Pollution and disproportionate exposure. Communities located near industrial facilities, waste disposal sites, or Heavily trafficked areas are often exposed to higher levels of air, water, and soil pollution. These communities are typically low-income or minority populations who may have less political power to advocate for cleaner environments. Environmental pollutants such as heavy metals, pesticides, and industrial chemicals have been linked to higher rates of cancer, respiratory diseases, developmental disorders, and other health problems in these communities. Access to clean resources. Environmental justice also addresses the inequitable access to clean water, healthy food, and safe living conditions. In many cases, disadvantaged communities are more vulnerable to environmental degradation and climate change, making them less resilient to the impacts of disasters like floods, hurricanes, or heat waves. Environmental justice movements. Social and political movements for environmental justice seek to ensure that all people, regardless of race, ethnicity, or income, have access to a healthy environment. Efforts to promote environmental justice include advocating for policy changes, increasing community awareness, and ensuring equitable enforcement of environmental regulations. Chemists' role in environmental justice. Chemists can help identify and quantify environmental contaminants that disproportionately affect vulnerable communities. They can also work on the development of cleaner, greener technologies and solutions for pollution remediation. Additionally, chemists can contribute to community outreach and education efforts, working alongside environmental justice advocates to ensure that disadvantaged communities have the knowledge and resources to protect themselves from harmful pollutants. 10.3 The role of chemists in environmental protection. Chemists play a critical role in addressing environmental challenges through research, innovation, and the development of sustainable solutions. Their work is fundamental to advancing environmental protection, pollution prevention, and the management of natural resources. Pollution monitoring and assessment. Chemists develop and apply analytical techniques to detect, quantify, and analyze pollutants in the environment. These methods help identify sources of pollution, assess environmental health risks, and monitor the effectiveness of environmental policies and regulations. Green chemistry. Green chemistry focuses on designing chemical processes and products that are environmentally friendly, using renewable resources, reducing waste, and minimizing the use of toxic chemicals. Chemists contribute to the development of sustainable materials, eco-friendly solvents, and alternative energy sources. Waste treatment and remediation. Chemists design and implement techniques to treat and remediate environmental pollution. These methods may include the use of catalysts to break down harmful chemicals, bioremediation to degrade organic pollutants, or the development of new materials for filtering contaminants from water and air. Renewable energy. Chemists play a central role in developing alternative energy sources, such as solar cells, biofuels, and hydrogen energy. Their work aims to reduce the reliance on fossil fuels and to advance energy storage technologies that can Support the transition to a low-carbon economy. Policy and education. Chemists also contribute to the development of policies aimed at protecting the environment, such as regulations on air quality, water safety, and waste management. They can collaborate with governments, industries, and environmental organizations to ensure that science-based decisions are made for the benefit of both the environment and public health. Education and outreach are essential for promoting sustainability. Chemists can engage with communities, schools, and industries to raise awareness of environmental issues and encourage responsible behaviors that minimize environmental harm. 10.4 Future directions in environmental chemistry. The field of environmental chemistry is evolving rapidly in response to new challenges and scientific advancements. Future research and innovation will focus on developing more efficient, sustainable, and equitable solutions to environmental problems. Some key areas for future development include advanced pollution monitoring. The development of more sensitive and rapid methods for detecting pollutants, including real-time monitoring of air, water, and soil quality, will allow for better risk assessment and management of emerging contaminants. Remote sensing technologies, such as satellite imaging and drones, could revolutionize environmental monitoring, providing real-time data on large-scale environmental changes and pollution levels. Circular economy. A circular economy model, which emphasizes reusing, recycling, and reducing waste, will require chemists to develop new materials and processes that allow products to be reused or decomposed safely and efficiently. This could reduce the environmental impact of industries, promote sustainability, and decrease the amount of waste sent to landfills. Climate change mitigation and adaptation. Chemists will continue to contribute to the development of technologies that reduce greenhouse gas emissions, such as carbon capture and storage, CCS, sustainable energy production, and climate-resilient materials. Research into adaptation strategies, such as improving soil and water management to cope with extreme weather events, will be crucial to help communities and ecosystems adapt to climate change. Sustainable agriculture. Future research will focus on developing chemical processes that enable sustainable agricultural practices, such as precision farming techniques, bio-based fertilizers, and pest control methods that minimize environmental damage. Genetically engineered crops that are more resistant to drought and pests may also play a role in enhancing food security while reducing the environmental footprint of agriculture. Environmental justice and inclusivity. Advancing environmental justice will require chemists to work in partnership with communities to identify environmental risks and develop solutions that prioritize vulnerable populations. Research on the environmental health impacts of pollutants will help inform policies and interventions that promote fairness and equity. Greener chemical processes. The future of environmental chemistry will focus on designing greener chemical processes that minimize energy use, reduce waste, and use less toxic reagents. advancements in bio-based chemistry and the use of renewable feedstocks will play a crucial role in reducing the environmental footprint of the chemical industry. Conclusion: environmental chemistry faces numerous current challenges, from emerging contaminants to the need for environmental justice. Chemists play an integral role in monitoring, mitigating, and solving environmental problems through innovation and research. Moving forward, the future of environmental chemistry will be shaped by advancements in pollution monitoring, sustainable technologies, and a commitment to fostering equity and sustainability. By embracing these challenges, environmental chemists can continue to make meaningful contributions to the health of the planet and its inhabitants. 11. Conclusion and future perspectives. Environmental chemistry plays a pivotal role in addressing the pressing environmental issues of our time, from pollution to climate change and sustainability. As the world grapples with increasingly complex environmental challenges, the insights and innovations driven by environmental chemistry will continue to shape the path toward a healthier, more sustainable future. This section provides a summary of key concepts discussed throughout the text, highlights the role of environmental chemistry in addressing global challenges, and outlines future research areas that will be crucial for advancing the field. 11.1 Summary of key concepts. Throughout this course, we have explored fundamental and advanced topics in environmental chemistry, with a focus on understanding the chemical processes and interactions that shape the environment. Key concepts include environmental chemistry basics. We introduced the core principles of environmental chemistry, including the structure of atoms and molecules, chemical reactions, and the role of thermodynamics and kinetics in environmental processes. Chemical cycles and pollution. We examined the Earth's atmosphere, water systems, and soil chemistry, addressing the chemical properties of each and how pollution from industrial, agricultural, and urban sources affects these critical systems. Topics such as air pollution, greenhouse gases, water contamination, and soil erosion were discussed in depth. Toxicology and environmental contaminants. The impact of harmful chemicals on ecosystems and human health was explored, with particular attention to bioaccumulation, biomagnification, and the environmental and societal implications of hazardous substances like heavy metals, pesticides, and industrial waste. Green chemistry and sustainability. We focused on the principles of green chemistry, which promote sustainable practices in chemistry by reducing waste, using renewable resources, and designing processes with minimal environmental impact. Climate change and its chemical drivers. A significant portion of the course was dedicated to understanding the chemistry of climate change, including the role of greenhouse gases, the science of global warming, and international efforts to mitigate and adapt to climate change. Emerging issues in environmental chemistry. Topics like emerging contaminants, e.g., pharmaceuticals, microplastics, and PFAS, environmental justice, and the role of chemists in advocating for sustainability were explored in the context of current and future environmental challenges. 11.2 The role of environmental chemistry in global challenges. Environmental chemistry is at the forefront of solving many of the most critical global challenges. Pollution prevention and remediation, as human activity continues to introduce pollutants into the environment, environmental chemistry plays a central role in developing methods for detecting, assessing, and removing contaminants from air, water, and soil. Chemists develop advanced techniques for analyzing pollutants and design remediation strategies to restore ecosystems. Climate change mitigation. The field is vital in advancing technologies for mitigating climate change, such as carbon capture and storage, CCS, renewable energy production, and energy efficiency. Chemists also help design greener chemical processes and sustainable materials that reduce carbon footprints and contribute to long-term environmental sustainability. Public health protection, by studying the effects of chemicals on human health and ecosystems, environmental chemistry helps identify potential risks associated with exposure to toxic substances. It also provides the scientific foundation for environmental health policies and regulations to protect vulnerable populations and ecosystems. Sustainability and resource management. Environmental chemistry provides the tools needed to assess the impact of resource extraction, waste generation, and product life cycles. By developing more efficient methods for recycling, waste minimization, and resource recovery, chemists help to reduce the pressure on natural resources and contribute to the transition toward a circular economy. Environmental justice and equity. Chemists contribute to identifying and understanding how pollution disproportionately affects marginalized communities. Through research and community engagement, they work to develop solutions that ensure all populations have access to clean air, water, and soil, promoting social and environmental equity. In addressing these challenges, environmental chemistry provides both the knowledge and the tools needed to make informed decisions, protect human health, and ensure a sustainable future. 11.3 Future research areas in environmental chemistry. As global environmental issues continue to evolve, there are several critical research areas in environmental chemistry that hold the potential to shape the future of the field and address emerging challenges. Emerging contaminants and their detection. The continued identification and monitoring of emerging contaminants, such as microplastics, pharmaceuticals, and per- and polyfluoroalkyl substances, PFAS, is essential. Research will focus on developing more sensitive and cost-effective analytical techniques, as well as improving methods for removing these contaminants from the environment. Carbon capture, utilization, and storage, CCUS. As the world looks for ways to mitigate the impacts of climate change, research into CCUS technologies will be crucial. This includes developing more efficient methods for capturing carbon dioxide from the atmosphere or from industrial emissions and exploring how captured carbon can be used in other applications, e.g., in carbon-neutral products or fuels. Sustainable chemistry and green innovations. Future research will continue to advance green chemistry by designing more sustainable chemical processes, materials, and products. This includes creating environmentally friendly alternatives to toxic chemicals, developing renewable energy technologies, and designing processes that minimize waste and energy consumption. Nanotechnology in environmental chemistry. Nanomaterials offer new opportunities for improving environmental monitoring, remediation, and waste treatment. Research into their environmental impact, as well as their potential for cleaning up contaminants, e.g., using nanomaterials to degrade pollutants or absorb toxins, will be a critical area of study. Climate change adaptation and resilience. As the effects of climate change become more pronounced, future research will focus on developing adaptive strategies for vulnerable communities and ecosystems. Chemists will contribute by developing new materials and processes that can help mitigate the effects of extreme weather, sea level rise, and other climate impacts. Chemical and biological remediation techniques. Bioremediation, the use of microorganisms to degrade pollutants, is an area of growing interest. Research into improving the efficiency and applicability of bioremediation for a wide range of contaminants will help in cleaning up polluted environments and restoring ecosystems. Water purification and resource recovery. The development of more effective water purification technologies is critical, as access to clean water becomes an increasingly global challenge. This includes advancing membrane filtration, desalination, and other chemical methods to ensure the availability of safe drinking water. Additionally, the recovery of valuable resources from wastewater, e.g., through resource recovery technologies, will play a role in promoting sustainable water management. Environmental health and toxicology. The relationship between environmental pollutants and human health remains an area of intense study. Research will continue to explore how chemicals in the environment contribute to diseases, developmental issues, and other health problems. This includes examining how environmental exposure affects vulnerable populations and determining safe thresholds for exposure. Environmental policy and regulation. As science and technology continue to evolve, there is a need for continuous research into how best to regulate environmental practices. Future studies will focus on integrating environmental chemistry with environmental policy to ensure that regulations remain effective in addressing emerging risks while promoting sustainability. Conclusion. Environmental chemistry is an interdisciplinary field at the intersection of chemistry, environmental science, and policy, providing essential tools to understand and solve the environmental challenges of today and tomorrow. As we face global issues such as climate change, pollution, resource depletion, and environmental justice, environmental chemists will continue to lead the way in developing innovative solutions. The future of environmental chemistry lies in its ability to foster sustainable technologies, mitigate environmental damage, and ensure a more equitable and resilient planet. Through continued research, collaboration, and action, environmental chemistry will remain at the forefront of efforts to create a sustainable and healthy future for all. Dear students, on behalf of Triune Biblical University Global Extension USA, we would like to extend our heartfelt gratitude for your time and dedication in engaging with today's course lecture. We truly appreciate your commitment to furthering your education and deepening your understanding of the subject matter. At Triune Biblical University, we strive to provide high-quality, accessible learning experiences that inspire both personal growth and academic achievement. We hope that the knowledge shared during this session not only enhances your understanding but also equips you with the tools needed to apply these insights in real-world contexts. Your involvement in this learning journey is invaluable to us, and we are honored to be part of your academic and spiritual growth. As you continue to explore and expand your knowledge, remember that our faculty and staff are always here to support you every step of the way. Thank you for being an integral part of the Triune Biblical University community. We look forward to your continued success and engagement in the courses ahead. Wishing you all the best as you continue to grow in wisdom, knowledge, and understanding. With gratitude, Triune Biblical University Global Extension USA.